But you ought to think about it like 3 weeks away. I think better to think of it like 3 weeks away. Why do I say that? Of course, because spring break is one of those 4 weeks. Okay, so it's like it's 3 weeks away. It's just like the spacing between every 2 exams. And so, here's the deal. The next exam is over chapter 7, 8, 9, and 10, right? We just continue in sequence. 8, 9, and 10. Okay? No surprises there. Chapter 9. Right? So I feel like people have already asked me, like, ooh, that was a tough chapter. Is that the toughest chapter in this course? Chapter 5! Ooh, chapter 5 was a tough chapter. Is that the toughest chapter in this course? No. Actually, it's relative, all right? It's relative, it's subjective. I don't know what the answer is. But if there's a tough chapter, chapter 9 is certainly up there. Okay? Chapter 9 is a bear in terms of concept and also in terms of information you need to know. Right? So conceptual information and just voluminous information. It's a challenging one. Now what are we going to do this week? Not chapter 9, we're going to do chapter 8. But we are setting the stage, so to speak, for chapter 9 immediately after the break. Alright, so what do you do with that information? There's no written law or rule that says you can't be a little bit productive during the break and perhaps do a little bit of work and maybe get caught up or even get ahead. Hey, there's a thought, particularly if you're having trouble in a course, maybe perhaps this one, to get a little bit further along in the material. If you're still developing your kind of lecture-to-lecture study program, your time management, and whatever else. Okay, so I'm only going to say this once, all right, and then I'm done with it. But you could perhaps cut out a little bit of time over the break to study, but don't overshoot. So as the slides were not working, I don't know what happened. I'm going to restart it right now. I'm sure it will work now. Don't overshoot. Every single break and vacation and holiday of my education, undergrad and grad school, I, came home with the load of I'm going to do this and this and this and this, and I'm going to do this with my buddies, and I'm going to do this with my TV time and this, and nothing. Right? I mean, academically, nothing got done. Okay, so I think you know what I'm talking about. Don't overshoot. All right, take one thing. Take 2 things. Don't take 3, 4, 5, 6, 7 things, right? You know what I'm talking about, right? Take one thing.
No, it is not an app yet.
And if you get some portion of that accomplished, that's tremendous. That's tremendous. Okay? That's it. That's all I'm going to say about that. Questions about anything? That's really all I had. And we'll start chapter 8 here. We'll still no picture. Yeah. No, I've always been able to get it. Just started all right, so you have a mastering assignment due on Saturday. You have the next quiz due on Monday. All right. Now look, the mastering assignment is available. The quiz will be posted ASAP. You don't have to wait till Saturday to finish the mastering assignment. Obviously, after Wednesday, you'll have everything you need to complete that. You can finish the mastering assignment. You don't have to wait till Monday to finish the next quiz. In fact, why would you do that? After Wednesday, you'll have everything you need to complete that. Okay, so my recommendation is to complete work as quickly as possible. As long as it's already available to you. And get it off your desk. You have an intervention to finish by Saturday. You don't need to wait till Saturday to do that. You have until Saturday to do that. Okay, was there a question? Yeah, go ahead. Okay, guys, I can't hear the question, so please let me try that one more time. Yeah. So the question is, when will the grade for exam 2? Well, I usually tell people a week, so I guess we have our exam on Wednesday, so yeah. Yeah, I think by Wednesday, I would hope to have that available for you. Yeah, it's already being processed and being pretty close. Okay, anything else? Yeah, and by the way, on that topic, if we can start the viewing, then before the end of the week, I would like to do that. Okay? So the 28th of this month is the academic drop date. I guess that's the last thing I'll say. We can talk more about it as we go, but the short of it is if you're not passing the course, the drop date is the last day beyond which you can no longer drop a fall course. So if you're concerned about your grade in a course, you need to talk to people now, right? You need to talk to your faculty, you need to talk to your advisor, you need to talk to financial aid. You need to get those questions answered and then consider the possibility of dropping the course. If you're not passing a course, you should consider dropping and then saving your GPA, right? Dropping is not quitting, it's just cutting your losses, allowing you to focus on your remaining classes. Okay? We can talk more about it and best talk individually about this topic if you're concerned about your grade. Question? Folks, question about anything? Anything else? No? All right, well, I'm going to have to lecture here without visuals here in a moment, so barring that, anything else? Anything else? All right, let's see.
We should get dinner together.
Right, folks, while he is on that, I'm going to go ahead and get started. All right, so Chapter 8 is the focus of today's and this week's content. We'll begin Chapter 8 today and then complete it on Wednesday. All right, now if I fall behind because of a problem here, I can fall back on visuals that I can post online. Right? I do have some audio content that I can post for you, but let's go ahead and start anyway. So Chapter 8 is a primer for the upcoming two chapters, 9 and 10, which deal with metabolism, right? Specifically, respiration and photosynthesis, which are examples of metabolism. So chapter 8 is a really important chapter. It's kind of setting the stage again for these upcoming chapters. Two topics are covered in chapter 8. One is metabolism, right? What is that? And what's it about? Okay? And the other is enzymes. Okay, finally, we reach a point in the course where we formally talk about these supposedly indispensable tools for biochemistry that we call enzymes. Remember that, okay? So we'll talk about both of these in this chapter. Of course, beginning with metabolism. All right, so what is metabolism? Does anyone have a thought about what that means? Anyone? So when you hear that, I think you think about, something to do with exercise or digestion or something, right? Oh, that person has a high metabolism. Oh, I have a low metabolism. I have to really, exercise. It's simply the cell's biochemistry. It's all of the cell's chemistry put together. It's biochemistry. That's what it is. All right? And metabolism breaks down broadly into two categories, and those are anabolism, right? And what? Catabolism, right? These are the two main branches of metabolism. What does that mean? Well, anabolism is the means by which we build ourselves, right? We build biomolecules. We construct polymers, right? All of that. Biosynthesis, by name, biosynthesis. That's anabolism. And in order to do that, you need energy. It takes energy to build biomolecules. It takes energy to build your cell. Intuitive, I think. Right? It takes energy to build something. What is catabolism then? What does that mean?
Breakdown.
Breakdown, yeah, it's the opposite. It's breakdown of biomolecules, breakdown of nutrients consumed, which then releases their energy. Okay, anabolism requires energy, catabolism releases it. So I don't think at this point it's rocket science to recognize there's a one goes with the other kind of aspect to that, right? If catabolism provides energy, that could then be used for what? For anabolism. Right, so catabolism fuels anabolism. That's the relationship. Okay? Energy. Now I've used that term energy several times, and we have not defined energy in this course. Let's do that now. What does energy mean? Ability to do work. Yes, it's no different in biology than it is in any other scientific discipline. Ability to do work is what energy is. There's different forms of energy, right? You're familiar with energy that's based on position, the position of an object, for example, or structure. Energy contained within structure. What's the name for energy based on position or structure? Potential energy. Okay, very good. The energy in our biomolecules is a form of potential energy, right? Again, structure of biomolecules. That is a type of potential energy. And we can get even more specific, we can call it chemical energy. So the energy in chemicals is chemical energy, but it's a type of potential energy. Then there's energy that is involving movement, right? That's of course what? Kinetic energy, right? So that's another form of energy. An example of kinetic energy is heat. You think about heat resulting in movement, right? Thermal energy. That's an example of kinetic energy. Now I mentioned chemical energy and I mentioned heat because both of those relate to our metabolism. Both of those kind of tie into what our metabolism is about. All right? Okay, there's a discipline that's focused on energy and energy transformation. That's called thermodynamics. And so at this point, we're going to begin. I'm going to attempt a crash course in thermodynamics. Right, that sounds really impressive. Well, I mean, we've done this before. We had a crash course in organic chemistry. That wasn't that bad, right? Chapter 5 was a crash course in biochemistry, right? I don't think that was too bad either. So this is a crash course in physics, right? And I think it will be over and done with pretty quickly. Okay, so what is thermodynamics? It's the discipline of energy transformation, right? And I'll tell you out the gate, there's laws of thermodynamics that have kind of come out of studying energy transformation. I'd like you to know a couple of the first two laws of thermodynamics. The first one is that no matter how much you need energy, like how badly you need energy, all you can do is convert energy that is pre-existing, right? You can't create energy, is what it is. You can't create, you need energy, you can't create it. All you can do is convert energy. So the energy that's there may not be in a useful form, right? But then you can convert it, right? So in my slides, here is like an example from the everyday world, right? So water behind a dam. Water behind a dam, what kind of energy is that anyway? Potential energy, again, energy based on position, right? Water behind a dam is potential energy. So you could open a valve and then the water begins to flow. Ooh, flowing water, what kind of energy? Kinetic energy, okay, good. And that could then turn a water wheel. I guess that would be mechanical energy if you position electromagnets in the right way. You could create electrical energy, which then goes out into the world, right? Through electrical wiring and then into your home, where you have all sorts of objects and gadgets that again transform the energy, right? So a desk lamp, which converts it into light energy. A fan, right, which has a blade and converts it into mechanical energy again. Or maybe a battery charger, and then you're back to potential energy, right? Stored energy. Okay. So this is a variety of examples of the first law of thermodynamics. You can't make energy, but you can transform it into a form you can use. Right? The second law says whenever you transform energy, you lose a little bit in the form of heat. There's that again. Heat, a type of energy we said. You lose some energy as heat, and then heat increases molecular motions and actually increases disorder. Okay, that's the second law. So disorder is increasing. And there's a fancy schmancy name for disorder in thermodynamics. What is it called? Entropy, right? So entropy is increasing. That's the second law. Okay? Yeah, so and then a little jargon. I can just throw a little jargon on you, and then we're almost done with the thermodynamics, except for like the one big thing I want to talk about. Okay, so whatever you're studying in thermodynamics is called the system. Right? Whether that's the cell, could be the system, whether it's a single reaction, it's the system is what you're studying. All right? By reference, everything else is called the surroundings. So the system is what you're studying, and then everything else is the surroundings. Okay? And then I think there's a term for both the system and the surroundings. What is that? Yeah, it's universe. Okay, the systems plus the surroundings is the universe. This is not astronomy. Okay, if you are thinking we're going to start talking about, I don't know, nebula, my son is 1 year old and he's fascinated by Jupiter, right? I don't know, it has something to do with it maybe, but he's back Jupiter. No, you're going to be disappointed. It's just jargon. Okay, system plus surroundings is universe. Now, a system can be open or closed. A system can be open or closed, meaning either it allows energy in and out or does not. Okay, open means allows energy in and out. Okay? So what do you think? Cells are open or closed systems? Obviously open, right? We are open. We are consuming energy all the time. We need to, we must. Open system. Okay, so we are open systems, cells are open systems, thermodynamically speaking. All right, so now this gets interesting. So there's a concept in thermodynamics. So what are we interested in terms of energy? The portion of energy that's usable. And really this applies not only to biology, but chemistry or anything, or aerodynamics. You want to know what energy is usable, so you can make use of it. And that's called free energy. Free energy, aptly named, I think. It's usable. Free energy, right? Oh, so good. It's free. And what is the symbol? How do we symbolize free energy? Yeah, it's G. It's capital letter G for Dr. Gibbs, yeah, I guess, who worked out the principles of free energy and thermodynamics. I guess he's like the godfather of thermodynamics. Gibbs free energy. It's just free energy. It's usable. Okay? I would like you to know what free energy is, because it's going to be in biology as well. It's the usable energy. So we define free energy. We define free energy as the total energy, which is somehow symbolized by the letter H, minus the entropy, which is symbolized by what? Yeah, letter S, right, yeah. So H minus S. I looked this up in case somebody asked me, why is it H and S? And even now I can't remember. I looked it up and I still can't remember. You just remember, it's the total energy minus the entropy. And how much energy you're losing as heat or entropy is really magnified by temperature, right? So the temperature kind of will magnify what you're losing in terms of entropy. So the full equation is G equals H minus TS. You got it? TS. Okay, well, I'm going to take a look at that actually, and then it'll be a little bit easier. All right? Aha, it's also familiar now. We just talked about it. A lot slower. Yeah. Ah, okay. There we go. So there it is. H minus TS, right? What is H again? Yeah, total energy. But we want to know what is usable energy. So we have to subtract the entropy again, which is magnified by S. Okay, that's like an easy question for me to write and for you to nail out the part, right? Just memorize the formula. That's it. All right, so how can we make use of this concept of free energy? I'm going to tell you right now. So in biochemistry, free energy it is going to change. In each reaction, free energy will change, right? And I think you may know change is symbolized by the Greek letter delta, yeah. So delta G is the change in free energy for a chemical reaction. Okay, then we need a convention. Okay, how do you know what the change is? The free energy of the products minus the free energy of the reactants. Okay, that's the convention. Energy of the products minus energy of the reactants we define as the delta G. Okay, and you can think of two possibilities here, right? Either your reactants have so much energy and then the reaction releases energy, right? You do this on a lab bench and then suddenly there's heat generated, right? So the products have energy down here, right? Reactants have this much energy, products have this much energy. Okay, that's one possibility. The other possibility is the reactants have this much energy and the products what? Yeah, up here. And then you do this in the lab and then the beaker is cold. You guys done this before? Okay, this is a simple demonstration of the difference in free energy, or free energy change in the chemical reaction, right? So it could be like this, where the products have more energy. Okay, so if the products have less energy, like that, the delta G will be negative, right? This minus that is going to be negative. But if the products have more energy, it's like that, this minus this will be positive, right? So you need to know whether energy is released or absorbed simply by visualizing a delta G. Simply by seeing the sign of delta G, you can know. Okay? Fair enough? All right. It's suddenly quiet, right? Which is telling me, like, okay, no, I gotta listen now, I gotta listen now. Okay. Analogy, I think, is helpful here, right? So we're talking about chemical reactions, right? Again, where reactants and products have so much energy here being on the y-axis, right? Free energy on the y-axis, the reaction course being on the x-axis here. Okay, that is a little bit abstract, right? Unless you work in the lab and you feel heat and all this stuff, it's an abstraction. So just think of the ball again. The ball at the top of the hill has what? More or less energy? More, of course. And if it rolls down the hill, the energy is released. So a reaction, that releases energy, right, is just like a ball rolling down a hill. Okay? And what did we say? Delta G would be what? Okay, that's a connection you gotta make there. So it's this minus this. Small value, large value is going to be negative, of course. Another term we can say is exergonic. Exergonic energy is released. Exergonic, that's called. More jargon. The product is more stable than the reactant. The product is more stable than the reactant. It feels right. That's intuitive. Okay? We also call that a spontaneous or favorable reaction. A spontaneous, favorable reaction. Okay? These are all the jargon thermodynamically that we apply to such a process. Okay? And then again, there's the opposite, right? Where products have more energy than the reactants. Well, that's where you gotta push the ball what? Up the hill. Yeah. And here delta G is going to, this minus this will be positive, of course. And the process we say is endergonic. Absorbs energy. The outcome is less stable. And this is non-spontaneous or unfavorable reaction. Okay? Again, jargon to make your own. Question? Oops. Question? Okay, one more question I have then. We're almost done. What happens to the delta G when a chemical reaction is at equilibrium, reaches equilibrium? What's the answer? Yeah, it's zero. Yeah, there is no more change. There is no more no. At equilibrium, remember the rate forward and backward are equal, right? Delta G is then zero. No change in free energy. And the system is at a maximum stability at that point. And such a system can no longer do any work. All right? Does this seem to describe what cells are, delta G zero? No. No, we're always consuming energy, right? It's driving our biochemistry. Absolutely not what cells are, right? Well, let's put it this way. Living cells, anyway, are not at equilibrium. No. The only time we reach equilibrium is what? Right, when life ends, right, we stop consuming energy, all of our chemistry reaches an equilibrium, and then that, that is that, right? Okay. Any questions at this point? All right. If not, application then. That's it. Thermodynamics. Accomplished. Here's a biochemical reaction you've already seen before. Right? This is sucrose, and water is another reactant. The sucrose and water are reacting to make the products glucose and fructose. Haven't we seen that before? Maybe we saw it in reverse. We're making sucrose. Well, in any case, this is the opposite. Is this one a dehydration or a hydrolysis? Hydrolysis. Okay, good. Right. So remember, hydrolysis means breaking, right? Or cleaving with water, right? Hydrolysis. This is a hydrolysis. Okay, very good. See, most people got that one. Correct. Next question. Is this reaction exergonic or endergonic? Okay. Fewer people answering anyway. Interesting. So, it is in fact exergonic. Okay? It is, but only I think 2 people said that. I have something to say about that because I think I know why people got confused about this. So, what is sucrose, anyone? It's table sugar. We're breaking down table sugar. Is that going to require energy or is it going to release energy? Come on. Of course it's going to release. Sugar has energy. Energy is released. You break it down, it releases the energy. And by the way, we can put it on the product side. In order to understand if something's endergonic or exergonic, you can put energy in as a reactant or product. So we put it on the product side because it's exergonic. Okay, it's a good practice, I think. I'm going to do that. The reason I think this gave you pause, that this question, is because you were thinking about bonds. Okay? Yeah. Okay, so what is the story with bonds? When you break a bond, does that release energy or does that require energy? It requires energy, yes. Chemistry, you learn this. It takes energy to break bonds. That's true. Who am I to argue with chemistry, right? We're breaking a bond here. We're breaking a bond in water, for that matter. But aren't we forming bonds as well? Yeah, it takes energy to break bonds, and when bonds form, what happens? Release energy, right? Okay, we're breaking a bond in sucrose, we're breaking a bond in water, we're forming a bond. This part of water joining to glucose, we're forming a bond. The hydrogen with fructose. We're both breaking and forming bonds. Forget about the bonds. Okay, is my advice. Forget about the bonds. Rather, look at the big picture. This is sucrose, folks. We're hydrolyzing it. Is there any question this is going to release energy? There's not. That's intuitive. Okay? Look at the big picture here. All right? Fair enough? All right. Well, that, I guess, is our example, and now we can go on to apply free energy to metabolism. Right? Okay, very good. So as we said before, catabolism is going to provide energy, right? And anabolism requires it. So catabolism will essentially fuel anabolism, which is just makes sense. However, right, so that's exergonic, then, and anabolism will be endergonic. Right? We apply those terms now to these processes. But truth be told, there's a molecule that bridges catabolism and anabolism. This molecule is produced by catabolism, which is then used for anabolism. What is that bridge?
ATP.
What is that molecule? Is of course ATP. Okay, so that connects it. Catabolism makes ATP, which is used for anabolism. All right? I'm going to try really hard to put anything with energy, anything providing energy in a brilliant font. Okay, so you can think of that as having energy. All right, so let's talk about it. What is ATP and why is it energy? So remember that this is an acronym for adenosine triphosphate. And I told you this back in chapter 2, or chapter 4, excuse me, when I was telling you phosphates have energy, right? And the ATP's got 3 of them. Adenosine triphosphate. Okay, what is the adenosine here? So this is actually put together, it's a nucleotide. Adenosine triphosphate is a nucleotide, right? And this is one of the 4 that's used to make RNA. Adenosine triphosphate is used to make RNA. The base is adenine, A. Okay? And of course there are 3 phosphates, therefore triphosphate. Right, so let's take a look here. And obviously it's energy rich because of those phosphates that we said have energy. So here it is. And remember your nucleotide. Nucleotides, we said, have 3 parts, right? Base, sugar, and 1 or more phosphates. And we said that everything is connected to the sugar, remember? So the base here joined to the sugar at that location. The phosphates are joined to the sugar at that location. The sugar kind of holds everything together, okay? Adenosine refers to the base plus the sugar ribose. The ribose sugar. It's ribose. Base plus ribose, adenine plus ribose is adenosine. Okay? And this term is helpful because then we can specify exactly how many phosphates. Sometimes you have only 1 phosphate attached to adenosine, then you go adenosine monophosphate. A monophosphate. Sometimes you have 2 phosphates joined, and then it's adenosine what? Diphosphate, right? Or sometimes you might have all 3, and then it's adenosine triphosphate. I've never seen 4. I don't think it goes to that point. Okay? So you get what they're doing here, right? Little starburst because that has energy. What about ADP? It's got a little energy, right? And AMP would be the least energy, and so they didn't put anything on that. Okay? So yeah, why is this energy? How does it provide energy? So remind me, what is the charge of a phosphate group? It's negatively charged, right? It was one of our 2 acidic functional groups, the other one being the carboxyl group. It's negatively charged. Notice that hasn't changed, has it? All right, so this is a lot of negative charge all clustered together. And we said many times, opposites attract and like repels. Okay, so this is a like repels kind of situation, right? You put all that negative charge together, and what does it want to do? Well, it's come apart. Okay, you guys have to go home, play with magnets. If you can remember, this comes apart. But it can't. Because what? Because we got covalent bonds, which again is a strong chemical interaction. Okay, so these phosphates want nothing more than to come apart. And this is like a compressed spring at this point. but the bonds are holding it together. Okay, that's I think essentially the energy of ATP. If the phosphates are allowed to come apart, say by hydrolysis, that would then release the energy, release this compressed spring, all right? And hydrolysis, how else do we break things apart in biology is hydrolysis. So ATP plus water could become ADP, an inorganic phosphate. It's just the phosphate on the end there released. Okay, that's no longer connected to any carbon atoms, so it's not organic, it's inorganic. Inorganic phosphate. Okay? And then you better put energy on the product side because, yeah, that's going to release energy. Does this make sense? Yeah. Again, it's just releasing the spring at that point. All right, so yeah, we're saying hydrolysis of ATP is exergonic, using the jargon again. So then we could specify the delta G. So let's start with the sign, positive or negative? Negative. Okay, you want to be like that with that. Okay, oh, exergonic, negative. Exergonic, negative. Delta G is negative, yes. In order to get the value, however, you would need to measure this. You need to measure this reaction. I think in chemistry, isn't there something called a bomb calorimeter? Okay, oh gosh, you guys are the experts on that. But there's ways to run a reaction and then measure with accuracy the release of energy. So it's 7.3 for ATP hydrolysis, and I mean a mole of ATP now. 1 mole of ATP hydrolyzed releases, I guess 7,300 calories or 7.3 kilocalories. Okay, released. All right? Question? That's a good one to know because you see ATP hydrolysis again and again and again. So you just want to know negative 7.3 kilocalories per mole. Good? Okay. Well, yes.
So it's negative because it's releasing it?
It's negative because energy is exergon.
Okay.
Yeah.
So if it was like, if it was positive, then it'd be the other one.
Yeah. Yeah, so for example, if you were making ATP, that would require energy, wouldn't it? Yeah. Positive delta T. Okay, good. But how is it used? Would be the next question. All right, so you have an inkling here how we release the energy, but how is it used? So let's talk about that. Now, the process by which it's used has a name. It's called coupling. It's called coupling. Coupling. ATP hydrolysis is coupled to an inorganic reaction. Okay, let's take a look. Glutamic acid is one of the 20 amino acids. You don't have to remember, but I just tell you. Glutamic acid is one of those 20 amino acids. And glutamine is another of the 20 amino acids. Okay, so these are 2 of the 20. And when it comes to amino acids, either you can make it in your body, right? This is really for all life now. Either you can make you gotta make protein, right? Either you can make like the amino acids, or you might not. In which case you have to consume it. Okay, so I believe in the case of these 2, you can make glutamine, but you can't make glutamic acid. And then this is something you gotta consume then. You gotta get that in your diet. Okay? Okay. bottom line is, glutamic acid can be converted to glutamine through the addition of an amino group. Okay, that's all this is. Exergonic or endergonic? Endergonic. Notice the energy now on the reactant side. Moreover, the delta G is positive. 3.4 kilocalories per mole. So that's, if you didn't notice that, maybe you noticed the positive delta G there, okay? And that also says endergonic on the slide, doesn't it? All right, so how do we use ATP for such an endergonic reaction? Well, we do them together. We hydrolyze a mole of ATP in order to make a mole of glutamine. And then this energy could become this energy, right? This energy released could be utilized to do this reaction, okay? Now, numerically, is this not enough energy? Yeah, it is. We need 3.4 kilocalories per mole. How much do we have? I mean, if you hydrolyze a full mole of ATP, you have 7.3. You need 3.4, you have 7.3. Okay? So if you're ever asked about that, all you gotta do is like add these numbers. You can just look and see the number is bigger than that. It would be big one way, but another way you could just add the numbers, and if you get a negative value, you know you have enough energy, right? Because energy is still left over. Okay? So another way to test if you have enough energy, make sure this value is the negative. All right? Yeah, enough. It's enough. 1 mole of ATP provides enough to make 1 mole of glutamine. All right? All right. Yeah, this is a looks good on paper kind of thing, right? I was going to tell you how coupling works, and this is in principle now, but how does it work practically? Actually, well, I'll tell you. In such reactions, the phosphate that's liberated is going to be transferred to a reactant. You gotta imagine that. A phosphate of ATP is transferred to a reactant. And what that does is effectively give the energy to that reactant, which then enables it to do what it needs to do and then become the product we need. All right. So basically the phosphate becomes part of glutamic acid, then the phosphate is replaced by the amino group, and then we got glutamine. Okay? So this method of phosphorylation, it's called, is the means by which ATP is used. Okay? Phosphorylation. We say glutamic acid is phosphorylated. Okay? Does that make sense? I think there's a picture in your textbook, and I don't have it on a slide, but you can take a look. As always, the book is there to clarify everything. All right? Any questions about phosphorylation? Phosphorylation is how coupling works. Okay, pretty good. So what we're saying then is that we're going to hydrolyze ATP into ADP inorganic phosphate to do cellular work and things like chemical work, like making glutamine, which we call anabolism. But also things like transport work, like primary active transport, which runs on ATP, doesn't it? That pumping of the sodium and the potassium, that's ATP driven. Well, that's another use of ATP. Moving vesicles around the cell, that requires energy, actually. And that's driven by ATP. Okay? And still more, what we might call mechanical work. Things like beating a flagellum, right? If you're a sperm cell, you gotta, well, that's gonna need energy. A moving of pseudopodia if you're a macrophage, right? Muscle contraction, right? We've said requires energy from ATP. ATP is what's gonna do that. Cell division also requires energy, and again comes from ATP. So 3 types of work, at least I would say, is chemical work, transport work, mechanical work, all driven by ATP hydrolysis. Okay? And all of that is coupling. And all of those events involve phosphorylation of a substrate. Okay, phosphorylation of a biomolecule. Something gets phosphorylated in order to use that energy. And that's the means by which ATP is used. Which then begs the question, how do we get ATP? I mean, it's all about ATP, right? We just consume that? No. No, we can't consume ATP, not in much abundance, really. So what did we say? First law of thermodynamics. You can't get the energy you need, you can do what? You can transform it, right? All you can do is transform it. And so that's what's going to happen. We're going to transform the energy of the nutrients we consume into ATP, which means reattaching the phosphate to ADP. Okay, this is chapter 9 in a nutshell, by the way. There, chapter 9. It's just about how we reattach the phosphate to ADP to make ATP again. Right? Chapter 9 is about catabolism, right? Making ATP in order to do anabolism, right? Now, we talked about what anabolism is, right? Making ATP is what? Exergonic or endergonic? Endergonic, right? So we hydrolyze ATP because it's exergonic. Making ATP is endergonic. Yeah, and that's, again, the need for catabolism, right? So what is going to fuel that endergonic reaction? Well, catabolism, we call it catabolism. There's different forms. Cellular respiration is the best one. It's the most efficient, it makes the most ATP, but there's other ways, fermentation methods to make ATP, not as much, but also useful. Okay, and again, that's chapter 9, is how do we make ATP by respiration? How do we make ATP by fermentation? Okay? And that's coupling. In that case, we're coupling some exergonic catabolic process with the endergonic synthesis of ATP. We're coupling some exergonic catabolic process with the endergonic making of ATP. Okay, it's coupling, again, coupling. Okay? So coupling to use ATP, right? Coupling to use ATP, and also coupling to make ATP. Coupling. Alright? Exergonic driving the endergon. So a moment ago I asked you about the hydrolysis of sucrose. Was this exergonic or endergonic? Exergonic. Oh, very good. Okay, so now you know it, right? You could also say it's a spontaneous reaction. You could say it's a favorable reaction. Right? All of those apply. All of those are true. Okay, very good. Now, and I told you not to get caught up in the bonds, remember? Because if that's what you're doing, it becomes confusing. Again, this reaction involves both bond breaking and bond forming here and here, both breaking and forming, so don't get caught up in the bonds. Okay? Okay, good. So about that, all biochemical reactions are similar. All biochemical reactions involve both bond breaking and bond forming. Right? This is common among biochemical reactions, right? And even exergonic ones, right, like the hydrolysis of ATP, also requires bond breaking and bond forming. Okay? Why am I saying that? Well, I'm leading to something here. So ATP is great, right? Is it enough to make work happen in cells? I'm leading you, right? You want to say, yes, ATP, but no, because even with ATP hydrolysis, you still got to break bonds, right? Yeah, ATP hydrolysis is tremendous, but you got to break those bonds, right? You got to break the bonds. Breaking bonds requires energy, right? You know this, right? From chemistry. Okay, now is the time to remember that, right? Because all reactions, again, in biology, involve breaking and then bond forming. So all reactions are going to have, if you will, an energy barrier. Energy barrier. Energy barrier. It's a barrier that makes the reaction really slow. Unless you can overcome it. Okay, the barrier effectively makes the reaction slow. Now, if you can understand, you're like, what the heck is he? Wood. Burning wood. Exergonic or endergonic? Everybody, burning wood. Exergonic or endergonic? Of course that's exergonic, delta G negative. I'm not really impressed with this tremendous exergonic reaction here. This is wood, okay? Slow. Slow, right? Slow. Unless you do what?
Apply heat.
Okay, unless you do something to break those bonds, right? To get the reaction started. That's what I'm talking about, right? So this is an exergonic reaction, but I don't care. You still got to break the bonds, right? So if you can, relate it to something you know. Reactions, even the exergonic ones, even ones that are exergonic, have this energy barrier that must be overcome. Okay? And in a chemical reaction, we have a name for that. Okay, this energy barrier is called the energy of activation. The energy barrier you must overcome in all reactions is called the energy of activation, or E sub A. Okay? It will take the reactants to a point where they then readily react to become the products. Okay, it will take the reactants to what we call a transition state, where they will readily become products. Okay? Yeah, well that's a problem. That's why ATP is not enough. And remember how our biochemistry operates. Okay? So our biochemistry is not just one reaction, right? It's a reaction where you make a product which then serves as a reactant in a subsequent reaction which makes a product which then serves as a reactant in yet another reaction until you get to the final product you were trying to make all the time. So remember, our biochemistry occurs in pathways, we call them metabolic pathways, where reactions occur in series. Reactions in series, one after the other. So for this to happen, and this is the only way, again, we want D, but all we got is A. So we gotta make A to B and B to C and C to D. There's a barrier for each of these. Every reaction has this barrier. So how do we ensure that all of these reactions are going to happen fast enough? And that's something to understand, is our biochemistry, the chemistry of life, is fast. It is fast. It is a fast chemistry. And it's got to be fast. Biochemistry, as we know, it's got to be fast. If it's slow, it's just pointless. Okay? So how can we ensure the reactions happen fast enough, right? All right, so we can use a term here, right? So an agent that is needed to increase the rate of a reaction. An agent, be it physical or chemical, needed to increase the rate of the reaction is known as a what? Catalyst. Right. Catalyst. 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 We need a catalyst. And heat is indeed one example of a catalyst. Oh yeah. Yeah, we could add some heat to get this reaction going, right? A lit match, for example. We need a catalyst, okay? So we need that heat, for example, to get to that transition state so that the reaction can happen. Okay, we need a catalyst. Okay, so we have now seen the reaction of making glutamine, right? That was a practical consideration, something we needed to do. And that's going to happen somewhere in the cell, I guess in the cytosol, where we amass amino acids in large quantities so we can make protein, right? All these ribosomes, right? Making protein. So what do you think? Could we add heat, kind of add some heat here to get this reaction going and make glutamine? Is this a good idea? Add heat and we make glutamine. What's the problem with that? Yeah, so what is a cell made of? Protein. Yeah, good answer. Yeah, of course, it's got phospholipids in it, it's got fat, it has got carbohydrates in it, it's got all that other stuff too, but there's tremendous protein. It runs on protein. And what happens if you add heat to protein?
Denature.
It will unfold, yes, which we call denaturing. Yeah, okay. So if your bioconstruction is based on protein, then adding heat is not the best idea. Okay, we're not room temperature, right? So we can get away with a certain amount of heat, but not too much. or will denature our protein. Another problem with adding heat is which reaction are you going to speed up? Yeah, all of them. Thank you. If you add heat, it's going to accelerate all the biochemical reaction. Heat has no specificity. How can it? You can't apply heat to just that one, portion of the cell. That's no. How does that work? So two problems with heat: there's no specificity, and there's also the denaturing of the protein. Okay? Yeah. Very good. All right, so what's the solution? What are we building up to here? Yeah, we need a catalyst that will act specifically with specificity and also not damage the cell, right? And so what cells use are catalysts called enzymes, right? They are specific. They will operate on only one reaction. And they don't damage cells because they're not heat. Brilliant. So the only way for this to operate then is for every reaction, A to B, B to C, C to D, to have its own dedicated enzyme. So A to B is run by enzyme 1. B to C is run by enzyme 2. C to D? No, not 1 or 2. You need a third enzyme for that. Enzyme 3. Every reaction has its own enzyme. Okay, so now maybe you can begin to appreciate. We said that of all the biomolecules, proteins are the most important, and of all the proteins, enzymes, by far, are the most important of all biomolecules. Enzymes, yes. And how do they work? Well, that takes us to our next and final bullet, which is the need for catalysis. Enzymes. Which is a good topic for Wednesday. Any questions?